Hello and welcome back to Calculus 3, section 11.4, cross product. So we are continuing our streak of product and multiplication. We started with the scalar multiplication, which makes vectors longer or shorter. Then we did the dot product last time, where we take two vectors, multiply them, and get the scalar. Today, we are talking about the cross product, and the first difference between cross product and the dot product is that cross product is limited only to certain dimensions. Cross product does not work in 2D space, and it does work in 3D, and then it doesn't work in 4 or 5 or 6, it does work in 7 and so on. So we are only focusing obviously on 3D cross product. So only certain dimensions, you can do your research if you're interested in that kind of stuff, would have a cross product defined. Now, for the cross product, it's a procedure on how to calculate cross product, which I want to do first, and then we are going to see some definitions and obviously eventually the use of the cross product. So we're going to start first with the way to compute cross product. I am going to first say that the cross product, so cross product notation is U cross V is the vector, let's say ABC, crossed with the vector DEF. Now, to calculate the cross product, and order is important. We will see later with our properties that this is not commutative. So it's U cross V or V cross U. I mean, they will just be the negative of each other, but still, they're not the same. So to set up the cross product, you will first put the ijk unit vectors on top. Then you will put the vector U, which is ABC, and then you will put vector V, DEF. This is the standard setup. Row 1 in this matrix, row 1 is ijk, row 2 is the first vector in a cross, and then the row 3 is the second vector in the cross product. Now, this is a matrix. It's a square matrix, 3 by 3. Some of you already took linear algebra. You know how to find the determinant of 3 by 3 matrix. This is not the first time that we are going to actually need that concept. Later, we will learn Wronskian, and for change of variables in chapter 13, we will need the concept of the determinant of 3 by 3 matrix again. So now, if you haven't seen this procedure before, pay attention to know how to work out through this mess. So 3 by 3 matrix needs to be broken into 3 2 by 2 matrices, and then 2 by 2 matrices determinants are a very simple formula that you follow to solve. The way you come up with those first initial 3 is you start with I, so you will write I, and then this I will delete that row and column, and you are left with the determinant of BC EF. Then you are going to move over to J, but you need to put negative J. So that's one thing that you will have to memorize. Goes negative J there. Delete the row and column. The matrix that it's left is ACDF. And now go to K plus K. So the signs are plus, minus, plus for IJK.
Or any matrix?
So you pick now plus k, delete the row and column, and you have your A, B, D, E. This procedure reduced our 3 by 3 matrix to 3 2 by 2 matrices. Now to compute the determinant of each one of these, you will find the difference of diagonal products, or simply just run this symbol and follow the signs. So you have B times F. You see a little cross in the middle. So B times F, and then over here is flat, so it's minus, right? And then you have E times C. So this symbol, it kind of has everything in it. You will start B times F and then minus E times C. So what do we have? We have I hat times BF minus EC minus J times AF minus DC plus K hat times AE minus DB. I'm going to box this. This is the way to compute the cross product. Now, I just hope you will not be sitting there for 25 hours memorizing the last line, right? It's a pattern that by working out, 10 of these quickly, you pick up, so you don't have to sit and memorize the formula. You pick up the pattern visually and then just keep executing. So let's cross 1, -2, and 4 with 8, 1, and -3. The setup is IJK 1, -2, 4, 8, 1, -3. All right, so what do I have? I have I, and then I have the matrix. When I delete the row and column, I have a matrix -2, 4, 1, and -3. You will be skipping this step eventually, but now it's good to keep track of everything. So J deletes row and column, and we have 1, 8, 4, and -3. And then finally plus K, delete the row and column. You have 1, -2, 8, and 1. So generally, if you are making mistake, most likely you are forgetting a minus over here. That's the most of the time. So now we have -2 times -3, that's +6 minus 4. I'll write out the first one. So that's 6 minus 4 minus J, which is -3 minus 32, plus K, which is 1, minus and minus is plus 16. The answer is 2I. This is minus 35, so plus 35J hat plus 17K hat. You can also write it as the vector notation 2, 35, 17. The answer is a vector. Dot product answer is a scalar. Cross product answer is a vector. So that's what we have to compute. So now I'm just going to put another one of these for you to quickly practice, and then we'll move on. So let's have -2, 6, and 1 cross with, I don't know, 4, -3, and 2, whatever. So create a matrix. And solve. All right, so let's take a look. IJK with hats, -2, 6, 1, 4, -3, 2. So we have what? I, and then 6 times 2 is 12, plus 3 is 15. That's 15I. And then minus J, that's -4 minus 4, -8, so plus 8J. And then plus K, that's 6 minus 24, right? Yeah, 6 minus 24, that's negative 18. So the vector is 15, 8, negative 18. That's mechanics. You will be taking cross product many times. It has many applications. So let's take a look at the rest of the lecture. So let's start with the definition for the cross product. So given two non-zero vectors u and v in R3, the cross product u cross v is a vector with magnitude u cross v is equal to magnitude of u times the magnitude of v times the sine of the angle between.
What is R3?
I will explain that.
Real numbers again?
Yes, it is, but we have r cubed over here, which means it's three of those real number axes, one for x, one for y, and one for z. So we have one-dimensional number line from negative infinity to positive infinity labeled as all real numbers r. Then you have the two-dimensional space for x and a y, which is labeled as r squared, because you have negative infinity to infinity for x and negative infinity to positive infinity for y. So that's why the notation goes up by exponents of r. So as you can see, this definition follows very closely your dot product definition. For dot product, we use the cosine with these magnitudes of u and v, and in this case, we are using sine. I have to relog in. Okay. The most important use of this is to find an orthogonal vector. If I give you any two vectors in space, they have to be 3D vectors. If I give you any two 3D vectors in space, if you cross those two vectors, you will get a vector that is orthogonal, perpendicular to both original vectors. So what we do is, you remember the pain of us creating that with the dot product last time? We had that class that had that problem at the end. We could have just found one vector and do the cross product and we're done, right? But we didn't have that tool at the time, so yeah. So where do we begin? Well, let's immediately write this. So the vector u cross v is orthogonal to both u and v. Orthogonal to both vector u and vector v. We are going to also strengthen this once we understand that two vectors create a plane, and then when you cross those two vectors that create the plane, the vector that we will call normal vector is the vector that is perpendicular to the plane, but the other two vectors created the plane, therefore it is orthogonal to both of those vectors. So we will revisit this in a little bit different light as we move on. Okay. So we can find the angle, right? If we flip the formula that we have up there, we can find the angle between two vectors using the cross product. So I'll put old. We know that theta can be found as the inverse cosine of u dot v divided by magnitude of u, magnitude of v. These are all vectors, right? So that's old. Now, new method to find theta is inverse sine. And that inverse sine is going to be the magnitude of the cross product divided by individual, well, the product of individual magnitudes. So now you have two formulas. All right, so let's talk more about vectors. So if I have two vectors, u and v, then the vector that sticks up perpendicular to both of these is vector u cross v. And observe the right hand rule. As you wrap around the u cross v vector, so your thumb is pointing up in this picture, your fingers, as they bend around the vector u cross v, will first hit u and then will hit v, which is the reason why you have u cross v. If you want to do v cross u, then clearly you have to point your thumb down. So I'm still going to draw the same configuration for vector u and vector v. I don't want that to change. But what is going to change is that now v cross u is going to be below. Again, this is in 3D space, so you are supposed to grab this way because your fingers will first hit v and then hit u as you wrap around with your thumb pointing down with the right hand rule. And you see now it's a v cross u points down. So we are going to learn very soon, going to see the property which says that commutative property is not the cross product doesn't obey commutative property. However, u cross v is negative v cross u. So that's coming up. Also note that in a 3D system, right, we have our third-dimensional coordinate system x, y, z. We have three unit vectors I, j, and k. The cross of any two of these will give you the other one, right? So you just have to follow the right hand rule to see whether you're getting positive I or negative I, positive j or negative j. because it depends. It's different if you cross j cross k or k cross j, right? One is going to give you I, the other one is going to give you negative I as a vector, right? Space. So now when you can, if you do the cross product, actually, you know, the I, j, k deal, you have vector I to be 1, 0, 0, and vector j to be 0, 1, 0, and work goes here. Your answer will be 0, 0, 1, which is k vector. Just k. So try whatever combinations of these just for fun. And now we have the properties of the cross product. Number one. They call it the anti-commutative property. So U cross V is equal to negative V cross U. AU cross BV is AB times U cross V.
Is that also anti-commutative?
No, this is associative property because now A and U were associated to each other. Now A and B are associated right after the equal sign. So it's associative property. And then two distributive properties. U cross V plus W, that could also be minus there, is U cross V plus U cross W. Think of this as 3 times x minus 2 or x plus 2, right? You have 3x over here for multiplying the first two, and then plus 3 times 2, which is 6 for the second one. Do you all see the same thing actually?
Distributive property.
Yes, distributive property. One more distributive property for, if you know coffee, if you have U plus V cross with W, you have U cross W plus V cross W. And these are the properties of cross product. Now you can go ahead and prove any one of these for your 3 by 3. So you can use A, B, C for the first vector, and then D, E, F for the second vector, and then get them together to follow the formula. The angular acceleration. The path for linear motion, the path is given as the distance you measure as a straight line, or you can use Calculus 2 for the length of the curve to figure out if you're moving in a square root fashion or whatever. So you learn that your distance is measured in inches or meters or whatever. For angular velocity, your distance is measured as an angle in radians, and then you have angular velocity, which is radians per minute or hour, or revolutions per hour, because that takes time to spin, right? And then angular acceleration alpha. And the formulas are the same, you just plug in the other numbers. So now we are moving here to talk about the angular force. which is going to be called torque, and that torque is going to be denoted by a little tau, Greek letter tau. Torque.
Little tau.
Yes, tau. Yeah, tau. Exactly. So we have the definition for torque and definition for torque. So definition for this tau is going to be R cross F, which also can be found using the magnitude times the sine of the angle in between them. Yes?
You write the magnitude, that means like the final vector takes square root of all the components squared, right?
Yes. So now, let's talk about the door. So we are going to look at the door from the top perspective. So let's say we are removing the roof and the structure, and we're just going to look at the wall, cut the wall exactly at the top of the door so we can see the door from the top. So we have a wall, we have hinge over here, we have the door, and then we have another wall. So this is where the door is. Clearly it will have handles on this side because hinges are here. Why is the handle on this side?
Oh, so it's farther away, so less force. Farther away, so you have to use less force.
Yes. You want to make, well, you can do the experiment, right? You can make this, you can try it out, right? So at the door handle, you can all, well, you can't see, but the rest can see. So the door handle is the furthest away from the hinges, right? So we push over here, right? It goes easy because the length of the vector R, which is in our cross product, right, is making the force much larger, and the force is the rotational force which swings open the door. If you make that the radius shorter, then the number is smaller, and the force with which you are attacking the door is smaller, and you can open. So if you push over here, well, I'm incredibly strong, but you wouldn't be able to do it. The vector gets to be shorter, and then you can open. You know how many times you went to the wrong side of the door, right? Going to the store, right?
That's why they have the automatic doors now, right?
Yes, so everyone can feel special. I know.
Exactly.
So we have the force with which you are attacking the door. That's going to be F, and we are going to have the radius R, which is the length. And another concept, the one that they are discussing in a book, would be wrench. You can also think of the screwdriver. Oh, by the way, screwdriver, right? Screwdriver is interesting, right? Because it just exerts the torque. The ones with a bigger grip are easier to use than the ones with a smaller grip. And the radius is just that much larger, right? But it's also better grip. So,
The diameter.
The diameter is, yes. So that's that. But now, if you take a look at the wrench, right? You can also use they call it a breaker bar. So I don't know if you change your own brakes on a car. Usually those bolts that hold brakes are really tight. They might be rusty or so. You have to use a breaker bar to open those because the regular wrench won't do it. So when you draw the regular wrench right from the side, it will have this larger part here and the piece where you would put. What happened?
I was thinking of a long tool in my head. That's
Oh, this is called a hammer.
It's called a breaker bar just because it's a longer handle because you have a larger radius, so you can apply a larger force.
So you would grip it right there, and then this part is the part that spins, right, left and right, clockwise or counterclockwise, right? If you look at the wrench from the other perspective, I don't know.
What about?
So generally it would look like that. And then actually I don't know why I'm drawing these things. I can just do this. It's already done. So there you go. Right, that's the wrench. So you see the radius, the larger the wrench, right, the more force, the more torque you can put into tightening. Now you also have to be careful because if you over tighten, you can break the bolts, right? So that's
torque wrench.
Yes, they have a torque wrench, and you set the amount of torque, right, and the specifications from engineering. So if you're a mechanical engineer, you have to understand these things. Otherwise, you are doomed, right? You can't design things properly if you don't understand the way this works. So too much force, right, which is applied in circle. You see the torque, right? It's the force that acts circular but propels things forward. So just think about screws, not nails. Nails go straight in. They don't rotate in, right? The screws rotate in. So and bolts. The calculations for this, obviously, the force, right, with which you crank is given, which can be measured. And then you can measure the length of the wrench. So you have the two necessary vectors, and you just do the cross product of those two, and you have the torque. So the application is very easy in terms of computing it. It's just understanding the concept to make sure that you are applying Calculus 3. Every single page of this course is applicable to something that you can touch because it is a 3D calculus. So every single concept you can find.
Are there the torque in a car engine?
Yes.
Shaft?
Yes. Exactly. Yep. So, what do I want to say over here? Yes. So the force will be attacking this way, and you have your radius from right R, and then you can find the torque, which would be force cross radius. That doesn't matter. Radius cross force. Radius cross force. You know how to take the the cross product. So if things are given to you, just plug them in and be done. Computing cross products on orthogonal vectors. And then opening a laptop. A force of 1.5 pounds is applied in a direction perpendicular of a laptop at a distance of 10 inches from the hinge of the screen. Find the magnitude of the torque in feet per pound that is applied.
That's just an example of a problem.
That's the example of the applied problem. The rest is all compute the cross product and find the orthogonal vector by crossing the two that are given. Find the magnitude of the cross product. The rest is a joke. They give you two word problems, so 39 and 40. 39 is tightening a bolt, which is this. You just grind through that formula. And the second one is opening a laptop. We can model with his lap. Right? Everyone, pay attention the way the laptop opens. You see that? His finger is 10 inches away from the bottom of the screen. Yeah. So the force is applied perpendicular to the screen, which makes the screen, the top portion, rotate around hinges. Right? So as you open, right, you have the 10 inches over there, and you have the force that it's perpendicular, right, to the, what was that, 1.5 pounds. Pounds is a force, right? That's, that was one of the adjustments I had to make when I moved to US. You don't measure mass, measure force with which the mass is pushing the scale. So technically, when you buy 2-pound bananas, you pay for the force with which the mass of bananas push the scale. You're not paying for bananas.
So shouldn't you buy stuff at higher elevations?
That's true. If you buy bananas at the top of the Himalayan mountain, right, when the moon is above you, you pay less than if you just go across to the ShopRite. Yeah, it's a few cents, but still. I mean, it adds up over years.
Just make ShopRite in the Himalayan mountains and everyone will save money. It's an economic,
Well, no, that experiment is generally, expensive. It costs a few toes and things, so,
You have to, transport oxygen up there.
Yeah. Good. So that would be the cross product. I hope you're not disappointed. That's it. So next lecture after the break.